Good morning, students. Today I shall start the next part, that is part 4 of IR spectroscopy. So in my last lecture I had discussed about the vibrational energy levels of harmonic oscillator, that is when a diatomic molecule oscillates according to simple harmonic motion, then what is the value of energy we have already calculated, and that is called the harmonic oscillator, and that was like equation 9, 10 or equation 11. That is, value of energy is equal to V plus half h nu, or if nu is replaced by the term omega, then it is V plus half h omega, and when it is expressed in terms of wave number, then it comes like this. This is equation number 11. We can write here, this is equation 11. We have written all the terms here. What happens in actual case? The movement, that is vibration of a real oscillator, that is a diatomic molecule, is not perfectly harmonic, because for large displacement the restoring force becomes weaker, and for very large amplitude the bond between the atoms in a molecule must break, that is dissociation of bond will take place. Such a real oscillator is called harmonic oscillator, and the oscillation is called anharmonic oscillation, and the oscillator is called anharmonic oscillator. We have already calculated the value of potential energy for harmonic oscillator as V is equal to half kx square, where k is the force constant and x is the total displacement. This equation is for an oscillator undergoing simple harmonic motion, but for real oscillator, which is called as anharmonic oscillator, and the vibrations are not according to simple harmonic motion, for such type of oscillators, Morse proposed the value of potential energy as according to equation 13. That is, potential energy is equal to dE under bracket 1 minus e to the power minus beta x whole to the power 2. Here dE is the dissociation energy of the bond in equilibrium, x is equal to r minus re, already we have written as equation 2, and beta is a constant. Now in case of real oscillator, that is in case of anharmonic oscillator, we will have to put the value of potential energy not equal to half kx square, but we have to put the value of V according to Morse potential, and that is this value dE in the bracket 1 minus e to the power minus beta x whole to the power 2. And when this value of V, potential energy, is put, we get the solution for energy according to equation 14, that is V plus half omega e bar minus V plus half whole square omega e bar into xe, where xe is called anharmonicity constant. This xe, value of this xe is not given. If the value of xe is not given, then we put the value of xe is equal to 1, but the actual value of xe is approximately equal to 0.01, which is very small and is a positive value. Now putting the value of V is equal to 0, 1, 2, 3, etc. That is, here V is the vibrational quantum number. If you put the value of vibrational quantum number is equal to 0 or 1 or 2 or 3, we will get the different values of vibrational energy level. And the potential energy diagram for anharmonic oscillator according to equation 13 can be obtained like this figure. Here on the x-axis it is internuclear distance, and on the y-axis it is the potential energy. So this equation 13 is called Morse potential, and it is also called as Morse function, and the potential energy diagram or potential energy curve is called Morse potential energy curve. Now from the figure it is very clear that this much energy is the 0 point energy, this much energy is the dissociation energy,
and that is equal to dE minus 0 point energy, and this dE is equal to dissociation energy of the bond in equilibrium. This is also called as depth of Morse potential. From Morse potential energy curve, it is also clear that an harmonic oscillator, in case of an harmonic oscillator, energy levels are not always equispaced, but they come close together gradually as the vibrational quantum number increases. This is very clear from the figure. That is, when the vibrational quantum numbers as increases, at the initial stage it is approximately equally spaced, but as we go or as we increase the value of vibrational quantum number, the spacing gradually decreases, and after some time it becomes almost merged on each other, and we can say that a band is formed, a continuous band is formed. So a very important question here arises: what differences you observe in potential energy diagram of harmonic oscillator and anharmonic oscillator? Explain. Generally this question is asked. For answering this question, we will have to draw this diagram, and we will have to write the equation 13 and 14. We will have to write the equation 13 and equation 14, and we will have to draw this diagram, and then we will have to answer these points. So first point is, for lower value of V, the energy levels are equispaced. This is for lower value of V. For V is equal to 0, V is equal to 1, and V is equal to 2, the energy levels are equispaced. And for some higher values of V, energy level come close to each other. For some higher values, 3 is equal to 4, 5, the energy levels come close together in comparison to V is equal to 1, 2, etc. And for very high value of V, a continuous band is obtained. So this is a continuous, here it is a continuous band is obtained in this area. And for further, what happens? For large value of V, dissociation of bond occurs, which is represented by this line. This is the place where the dissociation is occurring. So for very large value of this V, dissociation occurs. So these are the points we observe when we draw the potential energy diagram according to Morse function or Morse potential energy. Now what will be the selection rule for this anharmonic oscillator? So for this anharmonic oscillator, the selection rule will be equal to delta V is equal to plus minus 1, comma, plus minus 2, comma, plus minus 3, etc. Now, according to this selection rule, what will be the allowed transitions? So these are the allowed transitions. V is equal to 0 to V is equal to 1, V is equal to 0 to V is equal to 2, V is equal to 0 to V is equal to 3, and so on. Here from V is equal to 1 to V is equal to 0, V is equal to 2 to V is equal to 0 can also take place, because here it is delta V is equal to plus minus 1 or plus minus 2 or plus minus 3. Now here it should be noted that the transition for V is equal to 0 to V is equal to 1, that is this first transition, this is much more intense in comparison to other transitions. Much more intense means when we print spectrum, then the brightness of the line is too much intense in comparison to the other transition. This is due to the maximum population of V is equal to 0 in comparison to the other vibrational energy levels. Because we know that in the ground state, the particles are in maximum population, and therefore the transition which occurs is maximum in number, and hence the intensity of the line in the spectrum is obtained maximum. It has been observed that the population of V is equal to 1 is about 1% of the population of V is equal to 0. This has been observed. Now, there are some terms like fundamental transition, first overtone, second overtone, third overtone, etc. or hot band. So, we will discuss this one by one. So, first term is here fundamental transition. I have written in the previous page that V is equal to 0 to V is equal to 1 is called fundamental transition, And for this fundamental transition, that is V is equal to 0 to V is equal to 1, we can write the change in energy like this: delta E is equal to E1 minus E0. That is, E1 means energy of second energy level and E0 means energy of first energy level. So according to our formula, just we have derived here in equation according to equation 14. According to equation 14, V plus half, V means vibrational quantum number value. So it is first 1, the value of V is equal to 1. So I have written here 1. So 1 plus half omega E bar minus 1 plus half whole square omega E bar into Xe, minus, for this term, V plus half means 0 plus half omega E minus 0 plus half to the power 2 omega E bar into Xe. Now we solve this equation. So this becomes 3 by 2 and this becomes 3 by 2 whole square. This becomes half and this becomes a half whole square of 1 by 2. So it becomes 1 by 4 and this becomes 9 by 4. So we combine the similar terms. So these two terms are taken together and these two terms are taken together. Here for these two values, the simplification is omega E bar, and here we take the common omega E bar into Xe. 9 by 4 minus 1 by 4 is inside the bracket, and when it is calculated, it is equal to 2. This will simplify into 2. So 2 into omega E bar into Xe. So this equation, that is delta E is equal to omega E bar 1 minus 2a. So this is the equation which is for fundamental transition. We get a question that what will be the equation for fundamental transition. Then we will write this equation, and suppose we have to solve the numericals relating to this equation. Then we have to know the value of Xe and also to know the value of omega E. If these two values are known, then the energy for the fundamental transition can be calculated. Also, I have written in my previous page, that is, normally we take the value of Xe as equal to 1, and if omega E's value is obtained anyhow, then we can calculate E value, that is the energy required for the fundamental transition. Now the next term is first overtone. So transition V is equal to 0 to V is equal to 2 is called the first overtone. Here the intensity is less than the intensity of fundamental transition, and we can calculate the energy required for this first overtone as delta E is equal to E2 minus E0. Again, using the same equation 14, we can write as, here I have written the fundamental equation for this. V prime means upper energy level and V double prime means lower energy level. This is upper energy level, this is lower energy level. Here for vibrational quantum number, we put the value of 2. Here upper energy level, these two values can be taken as 2, and for the lower energy values, vibrational lower energy values, we put the value of V as 0. So now again, after simplification, it becomes 5 by 2. It becomes 5 by 2 whole square, that is 25 by 4. Again it becomes half and it becomes 1 by 4. And if you simplify, then these two give 2 omega E and these two simplify 6 omega E Xe. So this is the equation for first overtone. Now for second overtone, similarly we can calculate for the transition V is equal to 0 to V is equal to 3, and the energy required for this transition, that is for the second overtone transition, delta E is equal to E3 minus E0. We again put the values in the same equation 14 as 3 plus half omega E bar minus 3 plus half of whole square omega E bar into Xe minus 0 plus half into omega E minus 0 plus half whole square omega E bar into Xe. After simplification, it becomes 7 by 2, it becomes 49 by 4, it becomes 1 by 2 and it becomes 1 by 4. After simplification, these two simplify as 3 and these two simplify as 12. Now taking common 3 omega E bar, it becomes 1 minus 4 Xe. Now the next term is hot band. The transition V is equal to 1 to V is equal to 2 is called hot band. This is also allowed transition because our selection rule is delta V is equal to, selection rule is delta V is equal to plus minus 1, plus minus 2, etc. So, when we take V is equal to 1 to V is equal to 2 transition, this is also according to the selection rule, and that is called also called as the allowed transition, and this transition is named as hot band, and this is identified by increasing the temperature. If due to the increase in temperature the intensity of peak is increased, then it will be called as hot band. So how hot band can be identified? Though this is the condition by which we find the hot band. If we increase the temperature and if we get the intensity more than before, then that transition is called as hot band. What is the reason for this? The reason for this is this one. Due to increase in temperature, particles in V is equal to 0 shift to V is equal to 1. V is equal to 0 is the lowest energy level. V is equal to 0 is the lowest energy level, and V1 is energy level just above the lowest energy level. So when we increase the temperature, particles present in V is equal to 0, that is in the lowest energy vibration energy level, jump to just upper energy level, that is V is equal to 1, and now the transition takes place from this energy level, that is V is equal to 1 to V is equal to 2, and this is called as hot band because the particles come to their, when temperature is decreased, the particle come to their ground state, means their own energy level, and again intensity is decreased. So this is how we can identify a hot band and what is the reason of this occurring of this hot band. Now, if we want to calculate the energy required for the hot band for transition from V is equal to 1 to V is equal to 2, then we can write as delta is equal to E2 minus E1, and again using equation 14 we can write 2 plus half omega E bar minus 2 plus half whole square omega E bar Xe minus 1 plus half, because this is lower energy level, 1 plus half omega E bar minus 1 plus half whole square omega E bar into Xe, and when we solve we get this type of equation, delta E is equal to omega E bar minus 4 omega E bar into Xe, and when we take common we get the equation omega E bar under bracket 1 minus 4 Xe. If we compare the above equation, this equation with the fundamental transition, that is delta is equal to omega E bar in the bracket 1 minus 2 Xe, then we find that these two relations are too much similar, and therefore the position of hot band is very much near to the fundamental transition. This is how we can identify where are these two transitions are taking place. So they are close to each other because they have a similar nature of equation, and diagrammatically it can also be represented like this. Suppose this is the lowest vibration energy level, this is the first, second, third, fourth, is equal to 1, 2, 3, 4, and according to selection rule we write that delta V is equal to plus minus 1 plus minus 2, so this is plus 1, delta V is equal to plus 1, this is delta V is equal to plus 2, this is delta V is equal to plus 3. Also, if transition takes place from V1 is equal to 0, V2 is equal to 0, V3 is equal to 0, then also it is according to selection rule, and this is called the fundamental transition. This one is called as first overtone, this one is called as second overtone. If we take here, this will be called as the third overtone, and so on. And for hot band, this transition is V is equal to 1 to V is equal to 2. Reason we have already discussed that at ordinary condition means at room temperature, the maximum population is for V is equal to 0, that is most of the particle present in V is equal to 0. When we increase the temperature, then some of the particles jump to just higher energy level, that is V is equal to 1, and then transition takes place from V is equal to 1 to V is equal to 2, and this transition is called as hot band. So today I conclude here, and from onwards I shall start the part 5 of this chapter. Okay, thank you very much.